Great. Okay. So let's start. Today's topic, what I want to say is something about the both Einstein, oops, condensation, or just BEC. So there are three very famous macroscopic quantum phenomena, right? One is, okay, so basically, one is the superconductivity. Another one is superfluidity. And another one is the BEC. So it is not surprising that the quantum phenomenon is important at atomistic scale, like in hydrogen atom. It's actually quite surprising it will manifest in this large scale system, right? Of course, all these phenomena happens at low temperature. If the temperature is too high, then the thermal fluctuations will destroy every interesting quantum phenomena. So before start doing any problems, I would like to just refresh your memory, give you a very rough idea what is this BEC. So imagine, okay, this is the spectrum we have. Usually this BEC, it works for even for the non-interacting particles. Basically means my spectrum is the standard one p squared over 2m. Non-relativistic particles at some temperature, in general, it satisfies the both Einstein distribution, right? And so there's some particles, yeah. So for the lower energy states, there are more particles in general. If we decrease the temperature and when it reaches some critical point, then the finite number of particles will condense into the ground state. Usually we assume it's a k equal to 0 or p equal to 0. So when I say finite number of particles, I mean, by the way, as I assume the total number of particles in the system is capital N, which is of course proportional to the volume of our system. So here, and when I say finite number of particles condensed into this p equal to 0 state, I mean, N naught is also proportional to the volume of the system. That means N naught divided by N is a finite number in the thermodynamic limit when I take my system to be infinite large, right? So that's basically the phenomenon of BEC. So this is a phase transition, and this is a very peculiar phase transition. The reason is this phase transition is driven by pure particle statistics. So what do I mean by that? So I will get, so the standard phase transition, for example, for a ferromagnet or antiferromagnet to paramagnet, the system is a spin system. There are interactions between spins. let's say, assume the interaction between spins is capital J. Then we know there's a phase transition. Assume this axis is a temperature T. There's some critical temperature Tc. Above this critical temperature, the thermal, the thermal fluctuation will dominate, and it's a disordered state. And in the lower temperature regime, so this spins will be ordered, and it's a ferro or anti-ferro. Assuming it's a ferro magnet, right? So in this kind of phase transition, there's a one crucial ingredient, which is the interaction between spins. If there's no interaction between the spins, there will be no such phase transition, because this interaction strength between spins will set the scale for your critical temperature, meaning that its critical temperature will proportional to your strength of this coupling. This kind of features is applicable for other kind of phase transitions, but in this BEC, it's very peculiar because we don't need any interactions between particles. It works also for the free particles. And it's a pure effect of the statistics. It's because your system is a boson system, and naturally when you cool down your system to some critical temperature, this will happen. So this is one thing I want to point out. So not their interactions. Yeah, okay, so another thing I want to say is, okay, of course, there are kind of two parts, right? One is the particles in the ground, in the excited state, and another part is the particles that condensed into the ground state. And the people usually call this part as the thermal clouds, or incoherent part. And call this part as just a condensate or whatever. It's a coherent part. And one could describe this condensate using a wave function. That means even though the total number of particles in this state is a naught, which is a finite, which is a large number, but it behaves like a one particle. And we can capture this with one wave function. That's why this condensate that's the reason why the condensate does not carry entropy. Entropy is a quantity that describes the degree of the disorder of the system, right? If you have kind of only one particle, there's no kind of notion of disorder of the system. Yeah, that's one thing. So what else I want to say beyond that? Yeah, I think that's what I want to remark on the BEC. Any questions about what I said so far?
How do all the particles share the same phase? Like, shouldn't it be some incoherent mixture of the ground state? Like, why do they?
That's why we call it coherent, right? They share the common phase. If they don't share the phase, there's a superfluid. Yeah, that's another story. Here, I just want to point it out. In general, yeah, in general, for the thermal cloud, it's very complicated, right? In general, for interacting particle system, you cannot describe the so many particles with one wave function. That's impossible. But here, by the way, the magnitude of this guy is n naught. Okay, so okay, right. So for this kind of BEC, the starting point is always I just write down what you learned in the class. Right. Maybe and sum over k epsilon k minus mu minus 1 and you know dx dp. This is the states, and also we have this. So we have v dp and the distribution. So we have like n divided by v equal to some integral. Like that. So one can, this is the density of the particles. So basically it means the density is a function of the, because we integrate out the P, so we only left with variable T, the temperature, and also the chemical potential. Of course, this also means the chemical potential is a function of the density and the temperature, right? And by simple argument that this guy must be positive, we know the potential, the chemical potential must be negative. And if we decrease the temperature, eventually at some critical temperature, this chemical potential will hit 0. And that's the transition point, right? That's what you learn in the class. Of course, everything is self-consistent at, within this regime. Your mu is 0 and the n naught is proportional to v. To say that they are self-consistent, we can simply write down the expression of n naught, right? N naught is nothing but exponential, the distribution function, remember, is minus mu minus 1, right? Right. So n naught is the number of particles in the ground state. So this epsilon equals 0 and beta minus mu minus 1. So to say indeed this mu equals 0, if mu equals 0, then the n naught must be kind of a proportional to the size of the system. You can solve for mu. So it's n naught minus 1. Right, I just so move this minus 1 becomes plus 1, and the whole purpose here is to solve mu as a function of n naught. So it's log 1 plus n naught equal to minus beta mu. So mu equal to minus kbt log 1 plus n naught. Because remember, n naught is proportional to the size of the system, which has large quantity. So this is small. So it's become like this. So in the thermodynamic limit, V goes to infinity, meaning that this n naught also goes to infinity. So it's 0. So everything is self-consistent. There's no, yeah. So this is another remark. I want to say. Okay, so the next question, which is actually a problem, is you need to, and let's prove at in 1 dimension and 2 dimension spatial dimension. With spectrum p squared over 2m, there is no BEC. Basically means BEC only happens in 3 dimension or higher. So to show that, first you need to know how to approach this problem, right? Before you start doing any calculation, you should have a brief idea. How would we approach this problem? So what we will do is to calculate the TC. If you get a reasonable TC, that means there's a BEC. For example, if you get a negative TC, meaning that at physical temperature regime, your chemical potential is always kind of a negative. It will never reach 0, meaning that there's no BEC, right? So the point is calculate TC. This is the only calculation you need to do to prove this statement, right? I hope it's clear. Okay, so let's work it out. Let's first look at the 2-dimensional case. Actually, in this situation, in the 2 dimension, the mu can be solved exactly as a function of temperature, as we will see. Okay, so the starting point is, just write down the equation. Now, it's 2 dimension instead of 3 dimension, right? So we have this beta epsilon p minus mu minus 1, right? So how to do that? Like the standard procedure, this integration over the coordinates give us the volume. In this case, is the area of the system. Let's still denote as V. That should be h squared. And this guy is nothing but 2 pi p dp, right? Okay, so just let us introduce a variable. It's just, it doesn't matter. Let's call it as it's very standard notation. Basically, this is a function mu. Right, now we convert dp to d epsilon. Basically, we just add what's the name? It's the density of state on before in front of this d epsilon, right? So how to achieve that? It's also easy, right? It's 2 pi p dp. We know this is just pi dp square, right? dp square is remember the spectrum looks like a p squared over 2m. So I times 2m and I divide by 2m. 2 pi 2m pi. This is the epsilon. So this guy becomes this guy. The epsilon 2m pi. Now we don't need to regard this epsilon p as a function of p. I regard this guy as just the epsilon, the variable, the energy, right? Is it clear so far? Good, good. Yeah, just some change of variables, right? By the way, this means the density of state in 2D for this spectrum is a constant, right? Yeah. In 3D, remember the density of state is proportional to epsilon to square root of epsilon. So in 2D, this is 3D. In 2D, it's a constant. Constant means independent of epsilon or epsilon zeros power. So, okay, let me factor out this 2m pi v. And also change the variables epsilon beta equal to x to make it dimensionless. Then it becomes this d epsilon becomes kbt dx. This guy becomes x. So I'm doing like step by step and to just show all the details so you can from kbt integration dx. Okay, I just said in 2D we can solve this integral exactly, but before doing that, let's look at the what is TC. To say what is TC, remember this is n, right? So n divided by volume give us the density, which is 2m pi kbt square. This integral, right? So at the critical temperature, mu goes to 0, right? Mu goes to 0 means the z is 1. Remember, is 1. So this guy becomes 1. This t with tc, this z becomes 1, so I just erase it. Right? So in principle, the tc is proportional to, this is just a constant, I really don't care. It's proportional to n, which is the density, which is also a constant, divided by this integral. But we notice that there is a divergence, logarithmic divergence at small x. Because at small x, some small x, this integrand becomes, exponential x minus 1 becomes x. So there's a log x 0, right? At the 0 point, it diverges, meaning that this integral is infinite, meaning that tc equal to 0. tc equal to 0 tells us this will not reach 0 at 0 temperature. So there's no window of the temperature for the BEC to happen. So that's the point. There's no BEC at 2 dimension. Is it clear what I'm saying here? Any questions? Okay, so if no question, let's solve this problem exactly. So here, I'm just calculate a specific point, meaning that's the critical point. In general, we can solve this mu, this z. as a function of temperature. So to do that, we only need to do this integral. Yes, or this integral. Let me. Yeah. So we only need to do this integral. How to do that? Some tricks. So this is the 1 over this guy. So we can rewrite it as some 1 minus the exponential minus x and the exponential minus x. We always like this exponential minus x, right? Because it will make my integration convergent. So that's why I make it like this. And we can ternary expand this 1 over 1 minus x. This x is this guy, x, which is 1 plus the exponential minus x plus the square plus dx, right? And we can write it as some series sum from 1 to infinity is the to the nth power exponential minus nx dx, right? And we switch the order of this sum with the integral. This is good when everything is convergent, and indeed in our case everything is convergent. This sum and also this integral n equal to 1 to infinity the n like this. Or as a physicist, we don't really care about the order. We can just switch it. If we run into trouble, we go back and check. Right. This integral is easy to do, which is 0 to infinity, which is n 1 over n. Like this. So the result of this integration is the sum of these terms. And we recognize that this sum is nothing but minus log 1 minus 3. So immediately we have the, we can plug this guy into here. We have small n the density equal to, let's call, never mind. There's a minus sign I add here and log 1 over 3. Let's call this positive constant as some alpha. I don't care, just some constant. And I can solve for z. So this is minus n alpha t equal to log 1 minus z. Remember, the purpose here is obtain the chemical potential as a function of t, so we can draw this curve, right? For all temperature. Then this is, let's take exponential on both sides. And they equal to 1 minus exponential minus alpha t. And this is exponential minus, sorry, exponential beta mu. So I take a log. So mu as a function of t is given by this And if you plot this curve, you would say is exactly like what I said before. At 0 temperature, it will reach 0. And for other temperatures, it's always negative. So this is a very special case that we can solve it rigorously for the whole temperature. Yeah, so any question about this two-dimensional situation? So here I give you all the steps just to show you this kind of very standard technique. You don't need to be afraid of this integrals. Okay, so if you understand this, then I'm pretty sure you can work out this one dimension by yourself, but in any case, let's do it very quickly. So in one spatial dimension, n equal to, now it's dp dx, exponential beta epsilon p minus mu minus 1. Right. And this integration over the system give us the length of the system, total length of the system. I still denote as V, it doesn't matter, just a rotation from minus infinity to plus infinity for P. So from 0 to infinity becomes dP. There's a 2 factor of 2. Now, similarly, I convert this dP to d epsilon, the energy, right? Remember, energy is this guy. So, so what's the result? You know, d epsilon dP give us m t dP, right? Oops, sorry. Yeah. So d epsilon equal to p over m dp. So dp equal to m divided by p d epsilon. This p is nothing but p equal to the square root of 2m square root of epsilon. So it's m square root of 2m. I hope I'm not making any mistake. Yeah, something like that. I think so. Right, I think it's correct. Yeah, so basically we have this, we replace this dp with this expression. What we really care about is whether the integral diverge or not, right? So let's see, let's use proportional tool. So I don't need to care about the constant. So it becomes epsilon d epsilon beta epsilon minus mu minus 1. And let's look at the critical temperature. So plug in, we get, so the the particle density give us epsilon -1. Remember mu equals 0, so this guy is 0. So we change the variable to x. which would give us x dx x minus 1. The prefactor is kbt square root of kbt c tc. So now let's look at this integral. So this integral, it also diverges at small x, right? Because this guy is x at a small x. So eventually at small x, we would have this, which is divergent, meaning that this integral equal to infinity. To make n to be finite, we need this tc to be 0. So only 0 times infinity has a chance to get a non-finite result. That's basically the argument. So in both 2 dimension and 1 dimension, there's no BEC for this quadratic spectrum. Is it clear so far? Let me know if you have any questions. So, okay, so now you may ask a general question, like in general, in spatial, in D dimension, and for spectrum proportional to A to the A's power. So what is the condition to have BEC, right? This would be a general question you want to ask. Okay, so let's drive it very quickly. Okay, so starting point is the same, n equal to dpd dxd. So I'm pretty sure you can work out by yourself, but let's do it together. So this integration over the x would give us the volume, right? Divided by volume. The left-hand side give us the density. The right-hand side is this guy. This integration over the momentum is from 0 to infinity, and the SD is the solid angle of a d-dimensional sphere, and PD minus 1 dp. Right. So SD equal to 4 pi for 3 dimension, and 2D for 2 dimension. Right. It's a constant. It's a numeric constant. Right, and epsilon beta minus 1, and we also want to calculate what is TC, and the TC mu equals 0. So we can just erase this mu. Focus on this integral. So let's also use the proportional and disregard this kind of a constant. Right, so it's just a PD minus dp epsilon, sorry, exponential to the beta epsilon p minus 1. So similarly, we want to convert this dp to d epsilon. Right? To achieve that, it's kind of a trick we usually use. We know the spectrum is proportional to p to the 8th power. So what I want is the p to the a minus 1 power in front of this dp. but to make it invariant, so it's 1 minus A. So this guy would give us, by the way, of course, physically we would assume this A is positive, meaning that at a smaller momentum, the energy is lower. So it's given by P D minus A. This is D epsilon. There are some prefactors I don't care. It's just like this. And now we convert this P into epsilon. We know the relation is P is proportional to epsilon to the 1 over A. So it's epsilon. Something like this. So we replace this expression. We replace this expression with this d epsilon. So we would get epsilon A d minus A d epsilon and beta epsilon minus 1. Of course, we can do this procedure epsilon beta times epsilon equal to x. This would give us integration x dx exponential x minus 1. And the prefactor here is kbt to the power of d over a. Right? This is TC, so it's TC. Now we want this guy to be convergent to make sure there's a BEC. So at small x, there's no divergence at large x because there will be an exponential decay, which will suppress the integral. It will always convergent at large x. So we only need to care about the small x region. So at a small x, it would give us so this is x. So this x cancel with this dx. So left with a d minus a 0. So the BEC condition is D is larger than A. Basically, the spatial dimension should be larger than the power of your spectrum. That's the condition. When D equal to A, this exponential becomes 0, meaning that there's a logarithmic divergence, right? When it's smaller than when D is smaller than A, this guy is some negative number, meaning that is some 1 over x, this kind of a power divergence. Yeah, so this is a condition. And of course, this agrees with our previous example. Like for epsilon equal to p squared, only when the spatial dimension larger than 2, we have BEC. Any questions for this part? I hope it's clear, and I will show you an example. I mean, this is one problem from previous exam. I think it's also a comprehensive exam problem. Basically, you can say consider relativistic conservative boson. The relation, basically, this is the spectrum and the power A equal to 1. And derive the condition for the Bose-Einstein condensation in 3D. basically you just need to calculate TC, which is, we know that as long as the spatial dimension is larger than 1, there's a BEC. So this TC is a finite number. The starting point is also the n equal to the integral, right? And the second question asks you to check whether there's a BEC in 2 dimension, right? The answer is yes, because 2 is larger than 1. And what is the highest dimension for both Einstein compensation does not occur. Basically, the D at in D equal to 1, in the 1-dimensional case, there is no BEC. That's the solution for this problem. Yeah, so that's what I prepared for today's discussion. And if you have no questions, feel free to go. If you have questions, please, you can stay here and we can discuss.